Good evening, everyone. Gary is sick this evening, so you have me as your host for Space Oddities, and I will be joined by Professor Matthew Sadagas, who is going to present a good amount of material going over a lot of the science that UAPx has done over the last 2 years since the expedition for so this work has been done since the film The Terror in the Sky was made off Catalina. So with that, I will bring Professor Matthew Sadagas with us. Matthew, can you hear us? All right. Looks like he might be having a little bit of technical difficulties. So we'll give him a minute to hopefully. Oh, there we go. Matthew,
hey,
welcome.
Good to be here. Sorry I dropped off there for a moment.
Well, better than Gary, because Gary, not only is he sick, but construction folks cut a fiber cable like a mile from his house. So he's sick and has no internet. So he's not even able to watch us tonight.
That's the worst combination. It's sick without internet. Just ask my kids.
Indeed. So tell us about what you're going to be sharing with us today.
So I'm going to be sharing some slides of presentations that I've already shown to SCU and SUOPs meetings, but usually crunched down where I have to rush through them because I've got only 20 minutes or 60 minutes when it's actually 2 hours of material, and I'm forced to go through, so quickly.
We do have 2 hours, so if you're able to stick around for that, it's better to get more material out there than less.
That's right. Yeah. So I'm ready when you are.
All righty.
So since my internet's a little bit, it was flaky there a moment ago, I'm going to stop my camera because we want to focus on my slides anyway. I'll turn my camera back on if there's like Q&A or like after my presentation. So I'm just going to stop my camera and switch to sharing screen. And you'll have to let me know if it's working.
Okay. Yep. I have your slides up. If you go full screen, there we go. And I will give the screen to you.
All right. So I'm going to be talking about the latest scientific news we have from UAPx, which has UAlbany scientists on it like me, also Kevin Knuth and Cecilia Levy. We've got Ben, who's our host. We have Matt Phelan. We have our president, Gary Faris. So UAPx has also other members, and there's lots of overlap also with other organizations. So we have Candy and Ralph Seeger, who are retired electrical engineers. And we've got also, they're both members of SCU, and me and Kevin are also members of SCU, and Rich Hoffman is, of course, the leader of SCU, but he's also a member of UAPx. You can see a sample of our website on the left, but on the right is our science team members, and you can see Ben is in the lower right-hand corner looking totally awesome. You look like you're piloting something.
Yeah. I actually was in that picture. That's a selfie from the cockpit.
Yeah. So we have a lot of skills, and we have different people. We have basically, Professor Cecilia Levy is our own Dana Scully. Kevin, I'd say, is a lot like Mulder. And so who am I? I think I'm a lot like Agent Doggett, who's skeptical, but then sees enough stuff. So if for fans of the X-Files, hopefully they get the various character references. But the important thing is that we have a spectrum of individuals who vary in their amount of what you could call belief, quote unquote, but that's a horrible word to use, and about how much different bars of proof in their own minds, and that's good. That's very healthy, because then you have, it's like Kirk, Spock, and McCoy. You have a dialectical conversation that can happen when we're collecting data and analyzing it. So the objectives of UAPx are to acquire data which fill in the gap in the scientific knowledge of UAP that stems from a lack of high quality unclassified data. We want to make our data as well as analysis results publicly available. We already have publications I'm going to talk about, and I'm going to be talking today about like what are the first examples of data that we're going to be sharing with people, because we can't just dump 5 terabytes of data on people, but we're going to start by sharing the raw data, uncompressed, on our number one most interesting potential anomaly or ambiguity. So but we do not release data until completion of publications that are peer reviewed in scientific journals. We have our first publication is close to that, but is not all the way there yet. So we want to combine existing hardware in new ways, as well as develop new sensors to accomplish those goals. And we are complementary to the countless other organizations, so many other UFO organizations, but not many others. There are some, of course, like the Galileo project, whose entire objective is to find new data, their own data, but there are also plenty of organizations that reanalyze historical UAP cases. We don't do that because we want to have, chain of custody and data provenance. So this is where you can go on the web. You can go to archive, ARXIV. This is the number, 2312.00558. So if you just type 2312.00558 into your browser, actually without all the other HTML and all that, this will take you to our the preprint of our paper, which right now does there's a third version already. So this slide is slightly out of date. It goes up to version 2. We have a third version that has some of the newer stuff that I'll be talking about in the second hour today. So first, I'm going to review what some people may have already seen, but going into a little bit more depth, because like as Ben said, because we have more time. So our preprints have been out since December of 2023. So that's before peer review. So it's been undergoing revisions. As I said, we're up to revision 3, which might be the last one. So if you read version 3, there's not going to be a significant change from that. That'll be the default if you go to this web page. We when we had the first version in December, so exactly a little bit more than a year from today, like 1 year and 3 days ago, we did have a press release. There wasn't much media interest. We emailed a ton of people. I personally emailed a ton of people, and it really didn't. There wasn't that much interest, not from the mainstream media or even from the UAP community, which was too bad. But we are working towards doing everything scientifically, and what that means is that if we find that nothing we saw was really conclusively something anomalous, we're going to be honest and say so. So it might be a blessing, actually, that we didn't get initially a lot of media interest, because we're going to try again when our paper is completely finished with peer review. So there's this famous quote from Galileo that I've seen repeatedly. I'm sure the Galileo project has used it, but I mean at physics conferences I've been to just in my day job field of dark matter. So Galileo once said to measure what is measurable and make measurable what is not so. So we have a 4-point ideal method to strive for. This is in our paper that I just referenced, but of course, very few people, and I can tell because given some of the stuff that's in our paper and given some of the things people have been saying in the UAP community, I can tell like pretty much nobody's read it. Well, it's up to like 40 some pages, but it's not going to take you more than, I think Ben said, half an hour, to read the whole thing. So I'm going to hit the highlights from the introductory part, where we talk about how we commission multiple cameras, multiple copies of other sensors, to capture the same phenomenon for different angles at high resolution. That was the goal. We did not achieve that for every ambiguity or anomaly I'm talking about. The purpose of this is for robust estimations using trigonometry of distance, size, speed, acceleration. One of my huge pet peeves, and of course you need precise instrument locations for that. That's Kevin Knuth's specialty. But what's one of my greatest pet peeves in UAP studies is people say, oh, I saw this object, it was 300 feet in diameter. How do you know that? That's impossible to know. It's literally impossible unless you have a second viewpoint and your two eyeballs don't count. They're not far away, far enough. And unless you have like a reference point. But even with a reference point, how do you know? Like, let's say, oh, you compared it to that cloud or mountain. Yeah, you don't know how far away that mountain is. You also don't know. And so we want to take, estimates of sizes of objects, speeds from eyewitness testimony that doesn't have, infrared or radar data back it up. Got to take that with a grain of salt. So coincidence timing is our other hallmark of our idealized method, is looking at anomalies across different sensors that occur at the quote unquote same time within some tight time window. We want to, of course, this will cost money, will require funding, and of course, everybody else has the same idea, but we want to eventually construct permanent or semi-permanent stations that have automated sensors to serve as near continuous data collection stations. But the key is to not be random about this. So we have a little bit different philosophy. Different groups have different ideas. We want to do hotspots, UAP hotspots. So we don't just want to say, there's no such thing as hotspots. It's all random. I don't think that's the case. When you account for things like population density, things like that, you can actually make a case. There have been papers on this, but just as important, we need data in control areas. So we need control areas where we've got our airplanes, birds, things like that, or another type of control even far away from airports and have nothing to make sure we don't catch anything. So corroboration of anomalies via public sources of data is a fourth important bullet point. We are actually really successful at this, especially part A, because we actually looked at Doppler weather radar data. And we also saw it. We couldn't get access, but we tried to find unclassified satellite imagery to corroborate or not corroborate, right, agnostically or skeptically our main potential anomaly. We also looked into global particle radiation detection networks. Didn't get much traction with that despite trying. But we did get some traction with 4A there, where we did get a lot of work done on the Doppler weather radar data. That's in our paper. It's one of our proudest, most unique things we have in UAPx is our analysis of the publicly available Doppler weather radar data. So that's a first in UAP studies, and we claim that in the paper. It's different from, for example, I know Robert Powell looked up like the radar for the Stevensville case in Texas. We mentioned that in the paper, but this is the first time that no FOIAs were required. We just used Doppler weather radar data to try to see if there was anything in the sky at the time of our of one of our detections. So our instrumentation was quite varied. We had visible light imagery. We used Ron Ulch's UFODAP during the first expedition. We found issues though with the software, but also the hardware, where the UFODAP, because it uses CMOS and not CCD, may not be perfectly adapted for a scientific expedition. It could be maybe useful for citizen science, but doesn't have the same absolute calibration of efficiencies as a CCD would have to be able to pull out the information. It's got an intelligent algorithm that tries a little bit too hard, and sometimes that can cause artifacts. So we also had infrared. You can see it on the left. That was a set of infrared cameras from Dave Mason of Seattle. And basically, we also had, that should not be confused with night vision because that's a slightly different wavelength of infrared. And then there was a software package that I developed actually called CTAP. The acronym comes from Jeremy McGowan, who came up with it. He's an acronym fast with acronyms. So custom target analysis protocol. This is software that I wrote, debugged. It's talked about extensively in the paper. It's explained. And that's another one of the things we're going to make public relatively soon, is the CTAP software that I created so that other people can use it in the community. Although I have to warn people, it's for nerds. It's for again with the X-Files episodes, if you're like one of the lone gunmen, then you can figure out how to use it. It's not like, oh, I'm interested in UFOs and I've got a video on Analyze, let me download this thing. No, you have to know how to use Unix, Linux, or it can work on a Mac as well. If you're a Windows user, you're out of luck, unless you install, of course, there's ways to do that. Windows 11, you install Linux. And so with CTAP, that is not for the faint of heart. So it's not supposed to be some general magical software that someone who doesn't know how to use computers, doesn't know computer programming, can just download and use. So it's going to take some care in releasing it, because we're immediately, people are not going to understand that. We're going to get flooded with 500 emails from people saying this is crap, they don't know how to use it. Even though if you read our paper, you'll see we were able to work some miracles with it and pull out, faint patches of pixels that were probably, that were really there, the tracking across the screen, probably distant airplanes, so show examples later. We had radiation detection. We had multiple different kinds. We had a radiation detector from Dave Mason. We also had the Cosmic Watch from MIT. Future sensing, the future sensor technologies, I mean, this is a wish list, because we need money for more expeditions, but we already have the ultraviolet camera that I've mentioned many, many times in many other talks, how it was used to photograph lightning in slow motion by the previous user, an atmospheric scientist, atmospheric science professor. We're excited about it, but we don't have anybody, we don't have people to come and learn to use it. We don't have students, we don't have paid interns. And so these are just a dream wish list. If we had money, we'd have electromagnetic sensors, piezoelectric acoustic sensors, which we do already have, and passive. Passive radar is something we're working towards with Gene Graniger. So Gene Graniger, this is a slide from Gene, not my slide, but I've shown it at the SCU SWAPS conferences. And so what Gene's been working on, so he's from Georgia Tech, and he's been looking for UAP types of targets in the Atlanta, Georgia airspace from low to high altitude. He's already detected some meteors. You can see examples here. And this is where, with a detection range of about 50 miles per altitude aircraft with large radar cross section, he's using basically, he's trying to capitalize passively on existing transmissions, like local HDTV transmitter. And so the idea is to look at the Doppler shift and base. And so this is not active radar where we're building our own, system, but this is a system that Gene's developing, and he's been working with not just UAPx, but also SCU and other organizations. He really wants to help people find an inexpensive way of adding radar detection also, which we did not have at all, of course, on our first expedition. This is one of our future reaches. So back to our past, though. So that was, again, future reach. So we had a UFO camera put together by I purchased from Ron Olds of UFO, and it has a lot of features we weren't able to use right away. There's this discone antenna for RF spectrum analysis. So people who are watched, Secrets of Skinwalker Ranch should be familiar with RF spectrum analysis. It was not calibrated, has not been used yet by UAPx. Similarly, the multi-sensor data acquisition unit package, I know that Ben's been working on trying to get that data from that. That's got like a accelerometer, GPS, ADS-B, and other things in there. So all we were able to get from the UFO from our first expedition, unfortunately, was just the images. We did not use this antenna. It looks cool, but we did not use the antenna or the sensor package. It couldn't record data, but we did get good visual data. And we so this is the camera that's at the heart of the system. So again, ignoring the antenna, sensor package is the Dahua 50232 camera. It's a CMOS, as I said earlier, and the cover here of the sensor package has been removed to display the internals, although I said it's not wasn't functional. But speaking of covers, one of the lessons that we learned is, even though the cover is good for things like obviously for hardening a camera against precipitation, but having a dome camera can result in all kinds of internal reflections that may cause problems in the data analysis and cause false positives of what you think is anomalous. So the bottom left is example daytime image of the Catalina channel. So for those of you not familiar with our first expedition, I imagine the people are by now. We went to Catalina, which is supposed to be a UAP hotspot, even going back in history from before the 2004 Nimitz encounter in that area. So with the Tic Tac. So the bottom right is the same view. So as a camera, the default angle is the same perspective, and that's at 4 a.m. on God, I've given this talk so many times, I should know this by memory. July 16th, I think it was, 2021. And that's where our famous dark spot appeared of unknown origin with bright pixel clusters within. Obviously, I'm going to come back to that later. So that was the visible light camera, which also the UFO app also had some basic night vision capability. But we also had our island team members, Dave Altman and Michael Hall, who passed away actually recently. I wanted to say Michael Hall was known as the paranormal lawyer, so I just want to say may he rest in peace. He was I visited him actually, and Dave Mason when I was in Seattle a few years ago for a conference. So Dave Altman and Michael Hall were our island team, and they caught this really cool object. It was this blurry spheroid that looked like a classic UFO, but for people who've already been following our updates, like on the UAPx website, we announced this already over a year ago, that we think this was probably the International Space Station, which sounds like a disappointment, but actually this was an incredible opportunity because it allowed us to see, could we, under very harsh conditions as in this was recorded, on an iPhone, held up to night vision goggles, which are shaking. Could we, under those conditions, and not blaming, the team members on the island is what we had to work with, but could we pull out the correct altitude and velocity? And we did, and we actually did. Now, as I said earlier, you can't tell if you don't have more than one perspective. We did have two perspectives, but too close together, just a few feet apart for this one incident. Could we determine the velocity? And we did. So there was, and the size as well. Again, though, there's degeneracy, as I mentioned earlier, but if you read our paper, you see if we assume the altitude of the ISS, we actually get the correct size of the ISS. So we're really proud of this because it shows that we're going to self-debunk anything like this that comes up. So ISS is one of those things. Starlink is another that's always coming up. So because of an issue with the first website we used didn't convert daylight savings time properly for internet from universal time to Pacific time, accounting for daylight savings, and so the ISS had been initially ruled out, and so once we corrected for that we went to a better website, the actual more official ISS website, which is still in beta test mode, but it shows the historical position. It's called isstracker.com. When we went to that better website, we actually got the correct conversion with daylight savings time taken into account, and we could see that depending on the visibility conditions, the visibility radius just barely clips Avalon and Catalina Island. So we also have a comparison, and this is also in our paper. You can compare. This looks what we saw is qualitatively very similar to what the ISS looks like in somebody else's night vision. In this case, black and white color scale instead of green. So we analyzed all these images, not the one I just showed you, because that one, as I said, shaky camera and a phone held up to binoculars, but with our stationary cameras, the FLIR in particular, and also the UFO-DAP, which are stationary except for rotations in the case of the UFO-DAP or slight adjustment of position for the FLIR cameras, then we for those cameras, so that was a total of, I believe it was 9 cameras, 8 cameras plus one 8 FLIR cameras plus the one UFO-DAP. We created software I mentioned earlier called CTAP, Custom Target Analysis Protocol, that is in gory detail. It's explained how the algorithm works in our paper. It is not magic. It is a completely simple, stupid algorithm. And I'm sure that similar things already exist and other people have better software, and that's fine. So one of the things that might happen when we release CTAP is a whole bunch of people say, this is stupid, I can do it better. And my response would be, go ahead then, please do, and share with the UFO community. So this is not anything genius or brilliant. It's literally just taking one frame and subtracting the digital values of the pixels, pixel by pixel, row by row, column by column, from one frame to the next frame to look for changes. So obviously you can already tell this algorithm is not going to work for a hovering object. That's not what it's designed for. It will easily pick up objects that are moving. Especially if they're moving quickly, that'll cause changes of pixels from one frame to another. But what was unique about CTAP is I think this is the first time this type of algorithm, at least publicly known, was applied to FLIR imagery. And so we were able to pull out things that were missed by the human eye. And then we had a simple algorithm for telling the difference between signal and noise. And it had to do with the standard deviation of the RGB pixels, which was strange. So there is no RGB, right? That's the internal FLIR camera software. So the RGB comes from conversion of temperature into a color scale. So there's only one piece of information, the temperature, that's turned into 3 pieces of information. And somewhere in there is something that can go wrong in that software conversion, and you can have different types of glitches, which we were able to characterize by looking at the standard deviation. And what we found was that what appeared to be obviously camera noise, bolometer discharges, or dead pixels, things like that. Well, dead pixels wouldn't change, but those types of phenomena had a very sharp peak of a very low standard deviation in when comparing the variance between the red, green, and blue values. These are the delta red, green, and blue values. So it's the change in the red, the green, the blue values from one frame to another. And we found that actually what appeared to be actual physical objects crossing the field of view, that this blue distribution was much fatter. So while there's overlap at low standard deviation, there's this huge parameter space here that enables to do a separation by integrating under these curves. So this looks like a neural network, but it's not a neural network. It's completely an analytic code. And so it's basically like a transparent AI, which is like the big thing now. And it really angers me because I had this idea 10 years ago and proposed it to the US Department of Energy. Nobody cared. But now it's like the hot thing is like explainable AI. And I'm like, oh yeah, I thought of that 10 years ago and nobody cared back then and I have no credit for it. But basically this is not a mysterious black box AI. It's a completely analytic algorithm. And so there's no mystery to the final classification. You can see here that when you integrate under these curves, you see there's a peak. Basically, we can form a discriminant that looks like a neural network. Here, 0 is background and 1 is signal. And I should be clear, signal does not mean UFO or UAP. Signal means it was a bird, a plane, a drone, a helicopter, was an actual thing in that the camera saw, as opposed to like glitches in the camera or clouds rolling by, for example. So that's what we mean by signal, is there's something crossing the field of view that's a physical object in the out there in the real world. So this is not a neural network, it's not machine learning, and it's not AI. You can maybe think of it as explainable AI, but really there's a classification score output that makes it most like a naive Bayesian classifier. So Bayesian, Bayesian statistics is an expertise of Professor Kevin Knuth, but I actually came up with this independently, but also kind of inspired by Kevin's work. So these are not symmetric, so not Gaussians, but we can fit these distributions to what are called skew Gaussians and create analytic functions, which are the solid lines that allow us to integrate and then determine. Then we can set we can set a boundary. We can set at 0.5, 0.9 to do discrimination between signal and background. So then we also had a radiation detector. So now I'm completely switching gears to have nothing to do with cameras, but I'm going through all the detectors after introducing them earlier. So the Cosmic Watch was developed at MIT for cosmic ray muons, but it also detects alphas, betas, gammas, neutrons, whatever, other types of particles. It does not tell you. Everybody always asks, what's the type of particle? We don't know. What's the direction? We don't know. Give us money and we'll find out, because we can then build better radiation detectors and more expensive ones. But this is the one we had, and this was a really good workhorse actually, because it found one of our most potentially interesting events together with the UFO DAP. So basically it counts, but it also tells you energy, which is nice. So everyone always talks about Geiger counters, and I laugh. I'm like, this is not the 1950s anymore. We have way better technology. So even though the Cosmic Watch itself, like I said, can be outclassed by more expensive things like crystal scintillators like sodium iodide, cesium iodide, things like that at high voltage, this is also more advanced than a Geiger counter that just goes click, 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 click. This actually goes, instead of click, click, it goes blink, 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 blink. It's got an LED, but more importantly, unlike a Geiger counter, it tells you the energy. So unlike a traditional Geiger counter, I mean, they have more modern ones that are USB. It actually has a USB thing and a micro SD card where you can actually save the data and look at it. So it's not just a live analysis type of tool. So why are we bringing radiation detectors along? Well, there's all kinds of stories. You can talk to the Tedesco brothers, Jerry and John. You can talk to, there's a whole UAP medical YouTube channel about claims of harm especially from ionizing radiation that's alleged to have come from UAP. You just need to look at things like the Cash-Landrum or inertial force incidents. So we do not, as I said, reanalyze old cases. We do not just take all eyewitness testimony and immediately accept it. But what we do on UAPx is, and Galileo Project, and I'm sure and other projects have the same philosophy. I know Wes Waters has written about this, is that basically you don't throw out historical UAP cases. You do not do that. I think some organizations might want to do that. We do not throw them out. What we do is we use the history to inspire what types of sensors we think might be useful. You can fake a camera. You cannot fake, a radiation incident. I mean, you could, but it's way harder than, playing with some CDI or Photoshop. So, and one of the other advantages of doing radiation detection is that's easier to analyze. The Cosmic Watch just produces text files that say at this time there was a hit of this energy. And as far as we know, no known craft produced measurable quantities of radiation, not at large distances. So we learned a lot of lessons on our first expedition deploying those sensors. So first, as I mentioned earlier, the UFODAP, while good for maybe for citizen science projects, is not reliable for object tracking identification, nor is the software capable of accessing the sensor package. So as a result, we got no ancillary data from the UFODAP like GPS location, ADS-B exchange. But even if we did have ADS-B, tracking just aircraft via transponders is not sufficient. One of the things we learned is we need to have, and I've got an app like this on my phone now. You need to know, where are all the satellites? Where are the rockets? And for satellites especially, where's Starlink? And where's the ISS? And what's really nice is there are apps for this. And in fact, one of these astronomy, like night sky apps, has told me before, like, there'll be a dot and it said like Russian Russian rocket launch. And I'm like, oh my God, look at that red dot, like on the app, and you look in the sky. And I'm like, so it's great. So it's not sufficient to just track aircraft. You need to track spacecraft as well, things in orbit. So multiple cameras, always a necessity. We had only one UFODAP. That's what we could afford. We had multiple FLIR cameras, which is good. But we also need multiple of everything. So you can't just have one UFO. If you have a UFODAP, you need 2 or 3. And they need to be far enough apart where you can actually do triangulation with reliable position resolution. And everything has to have a battery backup. We had a battery. We had cameras fail. We initially thought it was some, it was the woo thing where, UFOs shut down electronics. Turns out it had a much more mundane explanation. But we only had one of the FLIR cameras had a battery backup. So another lesson learned. Having many of those FLIR cameras, though, was not as beneficial as originally anticipated. They generated a large amount of data that was challenging to analyze. So instead, fewer, more modern, and better calibrated units would be optimal. And if lightweight, and I've shown off my lightweight one that I have, the FLIR One Pro for iPhone, it can be slewed on a gimbal to point in the same direction as the observable light camera. Obviously, you're not going to sacrifice a phone to do that, maybe an older phone or an iPad. But there's other options besides the FLIR One Pro, of course. So Kevin is working on transmission of angular information from one camera to another so that they can track together. We also learned all connectors must be RF shielded with metal against stray electromagnetic noise. All clocks need to be synchronized. We didn't even have minute level precision, which is terrible. Ideally, we need sub-second level, or at least 1 second, and checked up on. And device positions have to be recorded. Kevin's in charge. Is definitely knows what he's doing with this. This is a combination of GPS with a high precision GPS with a laser range finder for good position and angle determination. Where are your cameras? Where are they pointed? So obviously we have one most famous ambiguity, which was caught by the UFODAP. That's why movies called it Tear in the Sky, except not really. It was named by Carolyn Corey before this happened. So actually that's kind of cool. So this is a timeline of this event. If you're not familiar with it, I showed a teaser of it earlier. If this is your first time hearing about it, we just saw a mysterious black spot with bright white pixels in it. All of the times listed on the slide are Pacific PDT, Pacific Daylight Savings Time, Friday, July 16, 2021. So everybody was asleep. So because of filming during the day and early evening, during the late afternoon, early evening, late evening into the night. Our original plan was scrapped of like 24/7 shifts, and people would have night shifts, so like that didn't work. So everybody was asleep. So people asked like who saw this stuff, like so it was Jeremy found this, but that was months later, looking through actually the Cosmic Watch and UAP UFODAP data together. This was not like somebody wasn't up at 3:50 a.m. Unfortunately, that was the original plan, but everybody was asleep. So this was captured by the automated trigger of the UFODAP. So 3:14 a.m. a blank video without any obvious trigger. So that's like, I listed that first bullet because that's like a control data point. Then at 3:57:16, a diffuse dark spot appears at upper right. Its appearance may have triggered the UFODAP. So this is the 3:57:16 is the first interesting video. It has no well-defined edges. So at 3:57:27, the spot remained. The camera slewed, so it triggered again, but it was chasing an insect that was separate from this black spot. During the rotation, white spots that turn into black streaks appeared emanating from that spot, and the spot is not visible in later frames where the sky is well illuminated. So at 3:59:24, cameras again stationary, dots are visible within the spot for the entire length, and a new white dot appears towards the end. So there's also a lightning stage, and so actually not lightning, but lightning. 3:59:24 a.m. That's our most famous video of UAPx. But again, what we have to emphasize, I've emphasized this again and again, but it seems like hasn't really percolated through the UAP community, that it's not that simple, that we have other videos. If all we had was the 3:59:24, that would be a lot easier to explain or debunk, but it's part of this series of videos. There are at least three: 3:57:16, 27, 24. And then at 4:13 a.m., that's the first normal video after the incident. So 3:50, 4 o'clock. So there's this 10-minute span inside of which there are three videos, two of them separated only by seconds, 2 by 2 minutes, that have some strange features in them. So there's I have a link here to the YouTube video of my talk at the SCU conference when we were first analyzing this. I think that was in 2021, might have been 22. So we had we're at the SCU conference. There's a YouTube video of that, and so you can go there and get another. In that case, it's like a 2-hour, 45-minute version of this talk that focuses even more specifically on this is a strange dark spot and series of videos, but it's a little bit outdated, of course. So one of the things we're going to do today is I'm updating you to the latest information. And in this video, but then if you watch that if you go back and watch it, you can see how our knowledge evolved. So for example, in that video, we talk about the ISS incident, but we didn't know it was ISS, and we talk about it as a potential anomaly. So this video, the 3:50 a.m., when all of these are a few seconds each at the most. So I'm going to show the most relevant frames instead of playing the videos. But like I said, I will be sharing. UAPx has promised years ago we will eventually, as I said, share the video. I wouldn't be surprised if people who try to debunk or explain the video fail to read the entire UAPx paper. So I'm going to say now. I'm saying this now so I can show this video later. We can see this podcast episode, and so I can go ha later to all the skeptics who we do want to look at the video, but who then come up with an explanation that we already talk about in the UAPx paper. So that'll be hilarious. So I'm going to try to cover as much of those possible explanations today, but really the in-depth thing is to actually sit down and read our scientific paper. Because remember, UAPx, our number one thing is not podcasts like this or movies like A Tear in the Sky, but producing real scientific papers, and that takes time. Right, we're still not through peer review on our first paper, and it's now, let's see, 2000. So next summer would be 4 years after our expedition, but that's how science works. It's very, very, very slow. So we have here an example now of what this dark spot I was talking about. Also in the green circles here, the insect that comes in the second video, and the streaking of that dark spot happens in one of the videos. So all of these photos are in beautiful resolution, in almost full resolution in the PDF, as vector images in the PDF, or you download the PDF of our paper. But of course, we'll be providing the raw data eventually, as I said, because we're just waiting for the special issue of the journal that'll contain our paper and others like it, like a review of the field by Kevin. So above here are select images from the 187 frames of the 3:57:27 video, identified by frame number. So from frames 1 to 87, dark spot from the first video is still at the upper right. During the motion of the dome camera of the UFO, doesn't seem to move, at least initially. So that could mean, oh, then it must be a lens artifact. Or it could be due to its diffuse nature. It could be due to the algorithms, something with the software stabilization in the UFO DAP. But because it does eventually move with the camera, together with creating a streak of spots, and then the streaks again would suggest that actually, wait, okay, so then maybe it's not an artifact if it actually streaks together with the motion of the lights of the city lights, and does appear to do so, but not right away. So again, it's very, very ambiguous. So we've called, this was called before, the wormhole or wormhole-like phenomenon or portal. We have no evidence that it's any of those things, but we investigated a lot of different possibilities, especially the mundane and prosaic ones we could think of. So the bottom line is, it's a dark spot. You can't call it more than that, and it's got white dots. And they appear to have some behaviors. Like I said, you have some streaking in one of the videos. The streaks are black, not white, which is really strange. And the dots start to merge with the noise by frame 32 in the streaking video. So these are all of the frames of our 3:59:24 a.m. video. So this slide was 3:57:27. This is 3:59:24. This is at 20 frames per second. And so the temporal progression here is left to right, then down with 0.05, so 50 milliseconds in between. So the disadvantage of having an uncalibrated trigger system is we have no images immediately preceding and succeeding these frames, for these frames or any of the video frames. So it's impossible to see the immediate origins of this spot or the dots, or how did they leave. So continuous recording is one of the things we want to do in the future, or have a better system of buffered recording where we can rewind more. But these like fraction of a second videos are not even supposed to exist. These are inherently were really glitches in the triggering software potentially. So if we zoom in, so we have this all in our nice scientific paper. As we zoom in on the dark spot from the last slide, with we use now here on this slide green circles that indicate the appearance of a new dot. So a new dot appears between frames 12 and 13. At the same time, a black dot appears. So in a different spot that we had missed initially, because when you open the video, and this is why video analysis is so important, not just like watching a video on your screen. The title of like QuickTime or VLC or whatever video player you're using would like block this black spot. So we didn't even know when this white spot appears, this black spot does. So we don't know if that means there's something like fly from here to there quickly in one frame. That doesn't mean it's anomalous. Could be an insect, or could this be a camera glitch? We have no idea. We focus on the main issue of the dark spot, but we also documented any secondary anomalies here. The behavior of our dots is somewhat similar to that of historical transients observed in astronomical plates by Beatriz Villarreal of the Vasco Project. And she has numerous scientific papers on that work. So we did several analyses of this cluster of videos I've been talking about. The pixel intensity behavior suggests there might have been something moving like this, but it's really, really weak. It's very strong here. So when we do a pixel intensity correlation map, so this is over 12 of the 16 frames of the dark spot. This is as the dark spot was vanishing, leaving the white dots behind. There exists some correlation, but not much, between the cloud cover and the behavior of dark spot. So maybe this could imply an atmospheric effect, but maybe not, since it's so correlated around just that spot. Could also be, fly on the camera that then takes off. I'm going to talk more about that later. But this, again, does not explain all the features. It would explain a dark spot on the camera vanishing, but not the white spots. So here are 10 of the prosaic hypotheses we consider. These are our null hypotheses that we had. First, we had a false streak hole from aircraft with white dots, the aircraft or noise, or a natural cloud formation. This is least improbable in some sense. However, doesn't quite work when you look at the temperatures. It doesn't make sense. You wouldn't have super cooled water condensing. It just, the temperatures even at the high altitude were just too hot when we looked at the meteorological data. And there's also no aircraft in the area that was officially logged. We also looked at the possibility that it's just the stars through a normal hole. So in the cloud, so number 2 is kind of connected with number 1 because number 2 does not explain the whole, just the dots. And so we considered, flock of seagulls. Not going to be a flock of seagulls. We explained in the paper. It's just hilarious. But Starfield, we actually did the math and showed, look, it's the LA area. And you have to go look at the paper and check, but it's way too dense of a star field for like the Los Angeles / San Diego area. I mean, it's not a dark sky. And the star pattern also doesn't match. Number 3, this was a big one, is, it's a droplet of water evaporating. We did the math, and that would have taken a lot of heat, about 200 watts. And so even if we're off by an order of magnitude, let's say 20 watts, where did those 20 watts come from? How could the water droplet evaporate that quickly? Why wouldn't it be continuously shrinking and slowly decreasing in area? So we pretty thoroughly debunked the water drop evaporating. It also, again, you look at meteorological data, it doesn't make sense. We were too far up, too far away from the ocean for ocean spray. It was not realistic. Number 4, we took some actual data in my lab. Ben and I actually did this together to see, could it be a fly in the protective dome leaving. Ben also took a lot of data on the road using fly analogs as well himself. So that's one of the strongest possibilities still, even though it does not fit all of the data. So as I said earlier, before people start saying it's this or that, like number 3, it's a water droplet, and people start putting YouTube comments, maybe you should read the paper first and see why that's probably not the case. So number 4, fly. Number 5, could there be radiation? So one of the things I didn't mention yet in this talk, but if you see my earlier talks, is that we were clued into this strange dark spot camera image and video by looking at our radiation detector. So ionization from ionizing radiation like cosmic rays could light up CMOS pixels just like CCD, but number 5 is easy to debunk because that's not going to be focused in one area. Number 6, meteor breaking up or meteor shower. That does not explain everything. There was no meteor or bolide at the time. Number 7, camera noise. So this is number 7 combined with number 4 is kind of our best guess right now. And that's our best educated guess, and that's what we're sticking with, is probably a combination of 4 and 7. And I'll show you some of the data Ben and I took. So this could be camera noise in the dark environment. I mentioned the problems with the CMOS and with the software trying to be too cute and clever with its built-in algorithms. So this could be combined maybe with a residual effect from camera rotation earlier and explaining the white dots and streaks. 4 plus 7 still doesn't explain everything. So number 8 was already kind of mostly debunked by the correlation analysis I showed with the blue false color image. Number 9, I mean, there's nothing we can do about that. Military testing of a cluster of drones, I mean, it could be. Number 10 is reflection of lights in the camera dome from the nearby city lights, leading to the white dots inside of a water droplet, for instance. But we already know that doesn't work. So number 10 is unlikely, and it wouldn't explain why you didn't see the reflections of those lights on other nights when the cameras pointed the same direction. So if we assume it's not camera noise and it's in the sky, then Kevin Knuth did an analysis where he looked at the geometry, and he determined that if it is a real hole in the sky, he figured out where it is, how high and how wide. And then I did an analysis of the white dots to determine whether they could be noise, and they don't appear to be. They could be non-Poissonian noise, but they're not consistent with the Poissonian expectation. That's for those mathematically inclined where the variance and the mean are equal. And we see that when we do an example of noise, we can actually see that. We actually see the mean and the variance approximately equal. But when we look at examples of actual of what appear to be like real features, planes and birds and things like that, and various different cases, we actually see that our case of the white dots, white points inside the dark spot, are actually more consistent with the behavior of real objects being captured by the camera rather than noise. Now, there's all kinds of types of noise, so it doesn't have to be thermal noise, doesn't have to be shot noise. Could be some kind of non-Poissonian noise in a CMOS. That's absolutely possible, because this analysis was really assuming this is a CCD, but It's not really CCD, it's a CMOS. So we have to be a little bit careful, but it is interesting that when we look at noise, examples of noise, the noise does appear to be Poissonian or even a little bit worse. So I mentioned Doppler weather radar data very early on that we would look at public data sets, and we did. So we did a very intensive analysis. This was done by Matthew Phelan, and also a physicist who wants to remain anonymous. Right, there's still stigma in this topic, but one of the former Knuth Lab members. And there is some consistency where we found something that looks like something at maybe the right altitude, maybe the right distance in the radar data. So we almost called it done and said, wow, look, that's corroboration. But as good scientists, skeptical scientists, we went one level deeper and said, you know what? Okay, it looks like it's statistically significant, but what about the systematic error? What about the systematic of, okay, these objects look like separate from this, which is, clouds or something here, and there's a separate thing. Well, if you lower the threshold of the reflectivity in the Doppler weather radar analysis, lo and behold, those dots look like they're part of they're just part of the same, a cloud front. So so when you change the settings in our analysis, this made those points that we were initially very excited about at approximately the right time. We got really excited, but it turns out they weren't that interesting. But it's ambiguous. It's still ambiguous. So there does appear to be hits within a pair of rays defined by our ambiguity, where we think it was the sky based on Kevin's analysis. These hits are not particularly rare in this range, and there's a serious seasonal variation where you have much higher of what's called clutter reflectivity, or one of these other Doppler radar data variables, which I'm not very well versed in, not a radar expert. Neither are the people who analyze the data, but they talked to radar experts. Matt did, and the Kevin alum, and they discussed with radar experts who we put in our acknowledgments so that we knew what we were doing. But I provided the information, it's in the paper, but I can't explain what all these things mean anymore. I mean, I did at one point when writing the paper a year ago, but now I'm starting to forget some of the radar details. But the bottom line is it's like in this liminal gray space where it looks like, depending on how you look at it, we might have a couple interesting points that do seem to corroborate our 4 a.m. dark spot that suggests there's something physically in the sky, in the clouds. But then it doesn't look that special when you look at the broad perspective of different times and seasons, and different also slices, further north and further south, different slices of the sky. So back to the ISS now. So we pounded away at our UFODAP anomaly with the dark spot. I mentioned earlier that we did the trigonometry, and so here it is. I'm not going to go over it, but as I mentioned earlier, it's an important math exercise that serves as a foundation for future UAP work. We basically showed the velocity and the size are consistent with the ISS, about 6,000 meters per second and 110 meters. So pretty close within the error bars. This is all very consistent, and basically, even though it's just like dirt simple math, it's not even, we do a little bit of calculus here. There's some DDTs, but not much. It's simple algebra that could be done, by a middle schooler. And so therefore, why is it in our paper? Well, we did move it to an appendix because, it's kind of simple. But here's the thing. We originally had it in the main paper. Why? Because you can't believe the number of people I know, in the UAP community who don't know this trigonometry. And so we thought this is important to document so that, we're not going to force people to crack a math textbook and figure this out. We figured that having an illustrated example of a specific thing we thought was anomalous would be a great educational exercise in the trigonometry and how we did it. So now I've been flipping back and forth between our different anomalies and sensors. Now we're going back to the FLIR. So it's a wild ride today. So now back to FLIR. So we have all kinds of examples of things we caught in the FLIR. At different, these are examples from different cameras, days and times. So this is related to the last slide because ISS was in the night vision. Night vision is a kind of infrared. This is our forward-looking infrared cameras, FLIR from Mason. And these are example FLIR events from different cameras, days and times, in chronological order from left to right, row by row downward. word, of different events with CTAP detections in green circles. So that was the software I wrote. And A here, A is two different examples of what is a camera glitch of just a bunch of hot pixels firing off at once. We think that's called a bolometric discharge. B, I mentioned this earlier, how you can't even see it here. Like you can, even if I zoom in, you could barely see it. It takes a lot of patience to see. And initially we thought CTAP was broken and I needed to do more work on it. But CTAP was able to pull out this distant purple. Remember, it's false color. It's infrared, so it's the temperature. It's probably a distant airplane, and it crosses the screen, and it like goes across the FLIR logo by the letter M, and you can see it. You can't see it here, but like if you look at the video, you can actually see it's there, and it's tracked by the software. And then C is a pair of airplanes. So one's taking off, maybe from LAX, one's landing. D is an example of the moon, and in the inset, another example of the moon here. E, you can see one of the drones used to film us for the movie A Tear in the Sky. Pretty cool. Very nice. And then here, that's still unknown. We didn't spend much time on the paper. Talk about a lot in the movie. It looks like a bolometric discharge, but it's the wrong color. It's cold. There's this like little cold spot that appears here for a few frames. And that was also captured by CTAP. So G here, this gave us a lot of grief. And in the first talk I gave at SCU with Kevin, we thought it was objects falling into the ocean. And it turns out this is something called an NUC, or non-uniformity correction. So that's also just a type of FLIR camera glitch. H is a fun one where we found a helicopter. And I, this is an example of a parasailer, some guy paragliding. It's really cool because we can use these examples, just like the ISS, to test our algorithms for triangulation. So we have, I mentioned earlier, we have the FLIR 1 Pro now. So for iPhone, we only have one though, but you can see here how the moon and a plane look in it. It looks way better, much clearer. It's not just a blob. So we have a new miniature FLIR, and the resolution is now improved, and it's got a built-in CCD overlay with a second visible light camera. So we can see distant airplanes now overhead with obvious shapes now, and they're no longer generic white hot ellipsoids without any well-defined wings, which could lead to, like thinking something's unknown. So we've made we went back, and so that's what's new. But we also have old data to look at. Plenty of old data from not just the old FLIRs, but also the Cosmic Watch, where we looked at what were the highest energies and highest rates we detected from the Cosmic Watch. And if those of us familiar with the movie are familiar with Event Alpha, where we had a detection at 43.37 MeV, which looked very strange because it's one of the highest energies we recorded in the Cosmic Watch even before the expedition. It was very odd. It seemed to be coincident with the dark spot, but it's not an increase in rate of energy of radiation. It's only one event, and we're constantly bombarded by natural radiation at much higher values by many thousands, millions, billions, trillion times, and so we cannot. It by itself is not anomalous, but it becomes potentially interesting coupled to our dark spot, which we only saw in the UFODAP. So we didn't have the FLIR for that because the FLIR was down, as I said earlier, due to power failure. So if you look at the energy spectrum of cosmic rays, there does seem to be, but it happened more than once, which was the other weird thing on the expedition, is there does appear to be like a breaking of this trend of higher energies are less probable from natural occurring radiation. There does appear to be at least a couple bins here, and that's where our 40 MeV guy is. So we looked at explanations of this, like the sun, some kind of solar flare or coronal mass ejection. Didn't quite fit. So we did some statistics though. So we wanted to compare the rates, and we wanted to determine what's the probability that the Cosmic Watch had an accidental detection at the same time as the UFODAP. So let's say UFODAP has a glitch at the same time Cosmic Watch just has a random radiation event from naturally occurring radiation. So this is known as the accidental coincidence rate. So it's something particle physicists like me do all the time, and it's something that the UAPx paper introduces to UAP studies, we believe, for the first time. The idea of having multiple sensors where you have you do classification, you do statistics on whether what's a probability of two or more of your sensors having a normal statistical glitch, but at the same time. And so when we did this, we plugged in our numbers and we discovered we were wrong initially where we thought it was like a 1 in 1,000 chance. It turns out that when we do it properly, the odds, while low-ish 20%, that's nowhere near, like to declare something interesting, at least in physics, you need like way below 1%. So we found that basically there was a 20% chance that we would have a 43 MeV, a cosmic watch event at the same time as the UFO DAP just triggering on nonsense. So that sounds low, and so you might turn it around and be like, so it's an 80% chance. It's interesting. I'll take 80%. But again, we don't want to do that because that's not right. And Spock would not be impressed by that. So that's my Spock is not impressed meme, if you're familiar with that. So that's why I have Spock is not impressed here. It's 20% that's not impressive. And so we cannot conclude that our radiation event, as interesting as it is, that has anything to do with the UFO DAP event, which might have its own mundane explanation. So there are all kinds of systematic uncertainties. Again, I brought this up with the Doppler weather radar data. So there are systematics in the radiation analysis, and depending on how we look at it, that this 20% could go up or could go way down, because we want to consider other potential corroborations. We want to consider the fact that there's another high energy event, not as high at 357.19. If we conclude that, then the probability drops to 0.04%, much more interesting. So why didn't we do that in the paper and say, look, it's a 0.04% that it was accidental chance? Because then it becomes a slippery slope. Let's go grab the next highest energy event and see what the odds of that are. And so that's a little bit dangerous. So statistics are not as cut and dry as people may think, because there's still human bias in the choices you make of your event window and things like that. So our conclusions from the paper. So this is not the conclusion. This is the halfway conclusion because I'm an hour in. So what are the conclusions from our paper? And then I'm going to tell you some of the extra stuff that some of it is in appendices to the paper you can find in version 3. So conclusions from like basically the first and second versions of our paper is that in light of all the possibilities, our most intriguing event, the dark spot with white dots, it remains ambiguous. So altering certain interpretations changes the statistical significance of it. We have some potential explanations for it that I'm going to cover in the second half. More importantly, we suggest that all UAP researchers adopt some conventions. So UAP research is obviously not a quote-unquote new field, but new in the sense that we now have more scientists at universities jumping in and not hiding in the invisible college. A lot more people now are diving in. And so in order to build an actual field, this is one thing that's been missing from UAP studies for the past few decades, is you don't have people citing and referencing the other works. So we're hoping that people cite and reference each other, build upon each other. And we've got a suggestion for the field, which many people I'm sure will reject, but we hope it catches on. And that is to define an ambiguity that requires further study as a coincidence between two or more detectors at the level of statistical significance of 3 sigma, and a true anomaly requires 5 sigma, but it's got to be 2 or more detectors. One's not enough. Now there's still some interpretation there, because a 3 or 5 sigma in a camera, pixel value change could be anything, right? It could be an airplane. And so so for images, that's a little bit less cut and dry. For things like the radiation detector, this is a little bit clearer. And for some of our other sensors that are simpler than a video camera, it's a little bit clearer how to do this. So there's still some ambiguity on how to define these statistical benchmarks. But again, we hope that this is going to start pointing people in the right direction of applying statistical rigor to this field. So most of UAPx's ambiguous observations, I focus on, the dark spot and the ISS, and they ended up being identifiable. There's still an ambiguity in our recommendations themselves, like I just said, definition of number of sigma for video, we recommend to always have at least 2 of each type of sensor to help with that. So like with video, you want to have 2 video cameras. We had more than that, but different types doesn't count. You can't have like 8 FLIR cameras and 1 UFO app. You need to have multiple of each. You don't overdo it with one type of sensor. You have to, it's more important to have a variety of sensors that will all be recording different data about the same object and not just different flavors of visual. So our results thus far may be best labeled as null results. And that's fine, because the history of science teaches us the value of such results. At the present time, we still haven't found dark matter. There are historical examples like the Michelson-Morley experiment where they didn't find the ether. So if we had money, if we had funding, we'd love to have new excursions to more locations of alleged UAP hotspots, but to Catalina for reproducibility. If this dark spot is some kind of weird, wormhole, I hate using that term because, we don't have any evidence of such a incredibly exotic or speculative claim. We want to does it come back in the same location in the sky? So reproducibility is one of those things that's really hard to do in UAP studies. It's really lacking, but it's lacking because it's hard to do. That doesn't mean you give up and you don't try, though, especially if you have hotspots. So we want to include improvements to equipment and methods, and that includes improving based on both the equipment and our software analysis methods based on what we learned from our own past work, but that of everybody else. So we have a huge bibliography where we mention Harvey Rutledge and Project, what was it, Identification. I think we mentioned Project Hesdalin. We dive in and we don't just say, oh, and here's everybody else. We don't just reference them. We reference them in the paper where it's relevant. Like, we were inspired to do this sensor by this group. This sensor, that group did better. We did worse. We did better. They did worse. So we do comparison, contrast with dozens of present and past UFO data collection projects. So, Ben, I think I'd like to pause there because this is a halfway point in case there's any questions so far.
Sure thing, Matthew. So we don't have any comment or any questions yet in the chat. If anyone has any questions for Matthew, please put those in the chat and we can respond to them.
Is there anything you want to ask me?
I don't want to jump the gun. I want to leave it to you, Matthew. You're doing great. This is awesome stuff, and it's just so great to be able to hear it from you. So as soon as you're ready to keep on going, unless you needed a break.
No, we can forge ahead. I just wanted to see if there was any questions that have built up. That's all. So.
Yeah, if anyone does have a question, just drop it in the chat, and Matthew can handle them as they come.
So I also wanted to I have some acknowledgments, plenty of acknowledgments. So I'm not going to read them out. They're also in the paper. This is left over from SCU, I think, or from swaps where I had only 20 minutes. Note to self, I forgot to delete that tonight. Jump to slide 6152. We don't have to do that because I can go another hour. So now we're going to dive into what's new. So a lot of what you saw so far was old. Some of it was new, though. There were updates to a lot of that information. Even if you saw it a year ago, 2 years ago from us, still plenty of updates there. But now we're going to go into even more, like really newer stuff. So one thing to keep in mind with the philosophy, though, is so what's new from when, like, the first time we presented these results is that we are actually trying to get published in an academic journal. As I said, our paper is currently under peer review, but I think the reviews are so this actually bullet point is a little bit outdated because this is from the summer. From this year's summer, we got through all the reviews already, so I think we're pretty close to being done. And how are we going to continue bridging the gap between like academia and science? So why am I talking about bridging the gap? That was actually the theme of the SCU conference, the Scientific Coalition for UAP Studies, whom UAPx works with. I mentioned earlier we have crossover membership. They have a conference, Huntsville, Alabama, or on Zoom or hybrid. Pretty much every year. They're going to do it again next summer, I believe. And the theme last year was about bridging the gap. So this slide was specifically for that conference, but I kept it in for tonight because I think this is an important theme that SCU brought up with that Robert Powell and Rich Hoffman and the SCU board asked the question of how to bridge the gap between scientists, non-academic scientists, engineers, government. So we need more PhD scientists. We need engineers as well, but we need more PhD scientists, not just in physics. That's why I said the word science. It's not just physics. We need chemists, we need biologists, we need geography, geology. This is a multidisciplinary problem. We don't know what UAP are. Everybody thinks lots of people, not everybody, but I was exaggerating. Lots of people think, oh, they're alien craft. Maybe they are, maybe they aren't. Maybe some of them are, maybe some of them are something else. But regardless of what they are, whether they're extraterrestrial craft or the atmospheric phenomenon or some combination, there's going to be an interdisciplinary problem. We also need editors of journals willing to allow the topic. We're so glad that we seem to have made headway with the UAPx paper. Don't want to count our chickens yet, but we may be getting that actually published this year or very early in January. So like I said, only 3.5 years late, but science takes time and peer review takes time. We improve the paper enormously by having people read it, reread it. We have blind peer review, external peer review. That's how science works. Another thing I want to bring up that I have the soapbox today in this, this is a transitional slide to the other newer scientific stuff, is funding sources. I keep mentioning there's no money. How do we get private funding? Well, we need to consolidate existing organizations. So UAPx has already been talking about this. SCU has this in the title of their organization. The C stands for coalition. We want to start moving towards actual consolidation of not just organizations, but conferences. It's good to have a variety of conferences. That means the field is really burgeoning and healthy. But like I'm stuck where like people keep asking me, did I go to this conference? Did I go to that? I'm like, I can't go to 5 UFO conferences. Okay. Like I'm not made of money. So even if I'm like a named speaker, like I've been before, and Kevin, like I can't go to all these conferences because I got a family and I've got my like day job conferences to go through for my dark matter work. So it would be nice to do some consolidation of conferences, although diversity is healthy, and in-person is of course ideal. So these are just ideas I'm throwing out there to the whole community. And it's good to not have enforced themes. Like the USU conference I mentioned has a specific theme. It's good to be more inclusive and allow the social scientists and the physical scientists and kind of have maybe parallel sessions. This is what the Mixophone of Society for UAP Studies has been doing. And also you should allow, this was actually, this phrase here was directly kind of a little bit of a friendly ribbing of Rich Hoffman of SCU, where I said, you got to allow scientists to finish slides at the last minute. Don't ask for like, oh, well, this conference is in June, we need your slides in May. I'm like, no, that's not how it works. So scientists are very busy and we finish our talks in the last minute. So what beyond our first paper, what are the new results? So we exposed the UFO data, but like I said earlier, I did a lot of these studies with Ben, with our host tonight, Ben. We exposed the camera to radiation. That was a ton of fun. Wasn't that fun, Ben? That was a ton of fun.
Most definitely. When else have I gotten to play with radiation sources and see the physics lab at UAlbany?
Yeah. And yeah, you got to see my lab and Cecilia's. And yet we exposed the UFO data to radiation, to water, to heat, light, darkness, and fly analogs. The fly analog. God, I love that. You remember, Ben, I cut out a fly. I printed a fly, like a picture of a fly, and I cut it out. Oh, what fun we had. And then we're planning many new papers, one on colors, about UAP colors, one on colonization. So Kevin has one on this out already. I want to do a follow-up to Kevin's paper, and a dedicated paper publication about CTAP. So that will be very general, has nothing to do with UFOs, has nothing to do with aliens, like the colonization paper. And then there's another thing, and this is actually, big update today. Well, not really. It's kind of a couple months old news now, but I actually did finish a first draft of the crash paper. I'll talk about crash probabilities. So I did, for fun, want to throw out this slide where another new thing that happened since the first time presenting, me or Kevin were presenting the results, was that on Mick West's one of his forums, not one of his, I'm sorry, he's got his big thing is Metabunk, right? That one thing. This is not Mick West himself. I just want to stress I have a positive relationship with him, but just one of the random people on his forum said a whole bunch of like really ridiculous things. And this one I had to just put on public display. So whoever Ann K is, I hope you feel incredibly stupid right now if you haven't seen this already, because I said this SC already. But basically, this person said, I don't know any physics, and kinetic energy is mv squared. So number one, they forgot the 1/2. Number two, this has nothing to do. This is the wrong equation for kinetic energy and relativity. So basically, I love this sentence. So she says to me, a physicist, this is directly at me, at Shidagis, it says, is that she's talking, what is this? Einstein for dummies. Okay, Anne, Einstein for dummies, except you did not use the correct equation for kinetic energy and relativity. Maybe next time you should think about calling a physicist a dummy. Even if they work on UFOs, they're not necessarily crazy, Okay, they might know some stuff. And in fact, you don't know basic physics. So it's 1/2 mv squared. And first of all, secondly, that's wrong, because that's Newtonian kinetic energy. So this was in response to an article I wrote on Medium, which then migrated to the UAPx website. So we're not just writing scientific papers, that's the focus, but I also wrote a fun essay, and as did Kevin. He's also got one on the UAPx website, uapexpedition.org. And yeah, look, this might come across a little mean-spirited, but they were super mean to me on Metabunk. I couldn't find another post. Mick might have deleted it, but there's another post that literally said, Shidagis' knowledge of physics is poor. And it's like, I'm a professor of physics, and I have a PhD from the University of Chicago. I mean, that doesn't mean I'm not doing argument from authority. That doesn't mean I'm 100% right all the time, by no means. But you don't say a physicist is wrong on physics 101 and then proceed to get physics 101 wrong in your post. So I think Mick took down the other post where they really insulted me, like directly ad hominem. That got, I can't find it anymore, so I think he deleted it. Which, if he did, credit to him. Credit to him. And another thing on this is I was accused of being this long German word that I don't know how to pronounce. I know German has these long ass words like Schadenfreude is a Technologie, Glauben, yeah, like. Okay, German's awesome for that, by the way. But I was accused of believing technology will always win and we will figure things out. That's in the context of interstellar travel. And I just thought to myself, oh, you mean like the atomic bomb and air travel and human space travel and all the other things that skeptics used to say were impossible? But anyway, I digress. I had to use this opportunity to shame people, because I think this is the harm of Uber debunking. So skepticism is fine. It's totally 100% okay, and it's the right thing to do, to respectfully disagree with me. And if I say, for example, hey, you know what? I like the extraterrestrial hypothesis, and maybe UFOs could be aliens. One could say, oh, I disagree for X, Y, and Z. But it's not okay when it turns into, ad hominem attacks and taking things out of context and things like that. And it's not okay when, basically you are so skeptical that aliens could literally land in your backyard and you still wouldn't believe it. That is not skepticism. That's called debunking. So skepticism is sort of an agnosticism where you're open to the new idea, but you don't jump immediately to a new idea if it's not part of the current paradigm. So that's something new that happened. I think, when was this? 2022. So it's not new anymore, but this was new. This was after the expedition, after the movie, and but before our first paper draft. But now here's something old that Ben worked on. Here's something Ben worked on that is not in the paper, because we were worried that this is a little too woo, this is a little too out there, even though we concluded that the results were garbage. We still shied away from putting this in the paper, rightfully so, probably, because like I said, 40-some pages, not people aren't reading it already. So we had something called a quantum random number generator. This had been suggested to us by Christopher Altman. We used it. I'm glad we did, because then Ben was able to do this amazing analysis and found spikes in the quantum. So what is a quantum random number generator? So just briefly for people, is basically a random number generator that's actually random, because it uses either electrons, as in our case, or it uses background radiation. So it's actually random, unlike the pseudo-random number generators in computer programming languages. And quantum random number generators were made famous in psychic phenomenon studies. That I don't know what the hypothesis was, that some psychic paranormal shit happens and random numbers are no longer random. Like, don't ask me. I have no idea why those two things would be related, but claims have been made.
And again, our philosophy on UAPx, again, is not to discount even the crazy claims, but rather to apply the scientific method and test them. Do not discount things out of hand, and that includes the high strangeness of UAP, the UAP phenomenon or phenomena. So it turns out that at least one of these spikes, this one right here, that was a phone call. So that was a cell phone call. So lesson learned is this random number generator needs to be shielded because it's random, quote unquote, but it's got, you can have, it's still based on like flow of like electrons from atoms. And so you could have, radio frequency interference, things like that. And so lesson learned, got to shield that because you can have EMI, electromagnetic interference. So that's a lesson learned. And then this prolonged deviation, Ben was able to link to above average solar activity. So again, you're not gonna, these are not, this is not some woo space-time warping, whatchamacallit happening. But again, like I said, I'm glad we did it. I want to publish a paper on this. Actually, Ben, I feel really bad that we deleted that section, but I think we could try in the future in another journal. I think we should publish your work, especially because it's so skeptical. It actually debunks the spikes. And so I want to give credit where it's due because we had to delete this from the paper. So this is bonus material. People who don't go to this YouTube aren't watching this tonight will not know this. I might have mentioned this briefly at the SCU or SWAPS conference, but I was talking at top speed. If you think I'm talking fast now, no. That's me talking slowly tonight, believe it or not. I had to blast through this in 60 minutes at SCU, and I had to blast through this in 15 or 20 minutes at SWAPS twice. So yeah, it's because there's a lot of material because we did a crap ton of work, all of us. It's not just me. I'm speaking tonight, but I'm giving credit where due, to Ben on slide 33. So then there was another potential mystery. This was something that Jeremy had captured where there was an object that was seen in one of the cameras. I keep talking about the UFO app, and I never specified that it's a 2-camera system. We didn't always use the 2 cameras at once. One's an all-sky camera, one's a PTZ to rotate to what the all-sky sees. And during the same night of Wednesday, July 14th, so remember our dark spot was July 17th. July 14th is the ISS incident, but on that same night, Jeremy and the Osiris found an object, one camera, not the other. It's entirely, our final best guess is there could have been something in one of the lenses, maybe a crack or something that prevented from one camera from seeing the object but not the other. But when we go back and we look at footage that didn't make it into part of the movie, but that I saw that got shared with me, but that I can't share, publicly, there's a whole scene where Jeremy was calibrating with a laser pointer and showing he could see it in both cameras. So even though our final hypothesis that it's probably was not anything special, but just because it was seeable in one camera but not the other, but there's still ambiguity. So again, we have ambiguity that maybe there was something interesting that happened. So we saw an object, Jeremy saw an object in the film crew. They didn't see it with their eyes, but they saw it in one of the cameras but not the other. And the worst part about this that didn't let us publish this, I still wanted to put this in the paper. This is also missing from the final version of the paper because we don't have video of it. We have a video of a video, which is absurd, right? It's like, Jeremy Corbell style. We got a video of a video. We can't do that because that's not scientific data. And basically what happened was the UFO app, the way it was set up, is it needed one camera to trigger the other. And so the fact that one camera saw it but not the other, it was the wrong direction. So the first camera didn't tell the other one to trigger. So we can't do anything with this, unfortunately. But again, speaking of the UFO app from the last slide, we did do cameras. This is not for the fisheye, which we don't have, but the dome PTZ camera. We actually Ben and I. This is in my lab. This is the door between my lab and next door lab, which is Professor Cecilia Levy's lab. So she's my colleague and also co-author on the UAPx paper. So we put this dark. We put a fly analog, which was literally a picture of a fly. We printed it out, and we put it on, and then we blew it off the lens. And we could see some similar features to our famous tear in the sky. We haven't quantified this yet. We don't have time. We just presented this as an appendix to the paper. Again, we're all volunteers. We're not paid. So I didn't run my Poissonian noise analysis on this or anything like that. But qualitatively, this looks very similar to our tear in the sky. So our current best guess to what we saw was an insect taking off causing some form of non-Questonian camera noise. So can we perfectly replicate every video, all 3 of the strange videos and every feature? No. No, we cannot. So we cannot state definitively that it's not something anomalous, but we can't state definitively it's not a fly taking off. There were plenty of flies, I assure you, in that were constantly annoying us. But again, it's another one of those lessons learned. We should get to one of those like fly zapper things if we're going to be in an area like that. So I was going to play some videos, but I think, let me see, it's 9:30. I'm going to skip over that as I did before. We did lights. So Ben and I did a whole bunch of stuff. We did light, we did water droplet, we did more flies. Ben did a lot of videos. He has a lot of videos I have that he took when he was on the road in the American West, and did this under like dark night sky, as opposed to me doing it in the lab with him. So the water droplet test, we showed actually you could illuminate the dome with LEDs or lasers and get dynamic rescaling of the camera that does appear to explain some of the dark spot of our famous alleged anomaly. So the water droplet tests, I actually do have a video. This is from Ben. Ben, do you remember, where were you? What state is this in?
So this was done in Tacoma, Washington.
Mm-hmm. Oh.
And actually, this one, if you, let's see, if you play it again, okay, there we go. That right there.
Yeah.
Where you get what that flash is the water droplet being illuminated by an off-axis light source. So it shows some behaviors reminiscent of the hole observed during Catalina. So that's the droplet being illuminated, and you do start seeing individual pixels that are either hot or just fixed high and have longer persistence than around them. So this was the experiment before I did a fly analog test, and this one is close, but I think when we get to the next one, we'll see a little bit closer to what was observed in A Tear in the Sky.
So yeah, this is the original fly analog test. Is the next slide. You're right, because you've seen my slides are, I think. So now we've got a small object commensurate with the housewives placed on the camera by Ben during nighttime operation. Now I have to stress, and there's going to be another video I'm going to show, the reason why we think this is slightly more likely is because, remember, I stressed earlier that water droplets don't just disappear. And so the water droplet test did look very damning, but we think fly is slightly better because water doesn't just disappear. And so it disappears too fast to be a water droplet. Now, the caveat to that is, as Ben just said, there could have been some camera software shenanigans where the water droplet did evaporate slowly, but there was an illusion of it being instantaneous because of software shenanigans. And so water droplets not 100% ruled out, but fly seems to have many of the same features as water droplet, but without that downside of water droplet can't disappear that fast. So basically, what this video you're about to see shows the placement, and nobody, by the way, I think outside of maybe the SCU conference, maybe last summer, I don't think anyone's seen this video, because the only thing we put in our paper was this, because we can't put a video in a paper, so we showed some frames of this one in my lab. But the viewers tonight can see of the podcast our the fly analog test, again by Ben. So Ben, you want to talk us through what we're seeing?
Sure. So that's me placing the fly analog on the dome. The dome is being heavily illuminated by my headlamp. Now the headlamp is removed. So that's actually just the placement of it. So it doesn't show the do you have the next video, Matthew?
Let me see.
Okay, yeah, so that's probably it. The fly.
No, I do not, because I didn't want to show too many of the same thing. So I'm sorry, that's the only other one I have.
Okay, well, if this one shows the first half of the fly analog test, and it doesn't show the damming behavior of when that fly analog is blown off. So you'll see after it's no longer illuminated, kind of blends in with the background.
Mm-hmm.
It's when it's blown off that it then it elicits basically the same hot pixels, the dots within the darker region that I'm pretty confident that we're seeing dynamic scaling of a CMOS. So it's you're taking a scene and you're trying to scale the pixels in order for those pixels to have the most dynamic range and not be either floored or full well. So what it does is it's trying to rescale what the pixel range is based on the overall light or an averaged area of light on the CMOS sensor. And then when something changes, a large area change, you then also have some underlying noise, even with what looks like a flat field. And then when the scaling of the pixels changes, the noise can then get amplified. So you've got a few pixels that are a few counts higher and some that are a few counts lower. But those ones that are a few counts higher, when it changes the dynamic range, those can get ramped up to look like a hot pixel or a full well pixel. And at least that's my hypothesis as to what is both what we see with the fly analog and what was observed during the Catalina expedition.
So even though I don't have the other video from Tacoma, I think Site 35 shows some of the damming stuff you were talking about. You can see the green circles. That's where my software would trigger. That's like the biggest difference in pixels. But you can see some of that similar behavior that you were just describing. It's pretty damning, I think.
Yeah, definitely. And the only difference with this is if you look at this scene, you see a highly contrasting scene where you have the door is dark and then the surrounding area is very light. When we had the nighttime scene, both in Catalina and with the fly analog test, then you have a much more uniform dark field.
Mm-hmm.
So this test very well might have like where your software picked up the green circles where you've got the noise. It might have looked a lot more stark if it was against a full dark field.
Yep, that's right. So that's what we think probably happened. Doesn't explain all the features of the 3 videos, but slide 41 pretty much sums it up. So I said I would come back to this dynamic scaling, and Ben mentioned it already. So there's an algorithm proprietary to manufacture, but is generally understood. And Ben just summarized. He anticipated my next few bullets, which is perfect. We think alike. So it's you can read it right there. Night vision mode, especially, is inherently noisy in this type of camera, and there can be amplifications of noise, as Ben just explained. So our prosaic explanation is a near field momentary aberration, for example, an insect that induced camera behavior resulting in the apparent anomaly. So we think this doesn't explain like, well, what about the radiation? It's a radioactive fly, but remember there was a 20% chance of that just being statistically by accident. So we didn't stop there. Because lots of people were, because of that coincidence with radiation, lots of people were like, oh, hey, could there be radiation? It's those crazy UFOs, flying around producing radiation. Well, we investigated this. And to the best of our knowledge, this was never done for CMOS. It turns out I did find, I think if UFO people have a community knows about, they know Maya Cowan. She's an anthropology graduate student at Binghamton. She found a paper. It's too late. I want to add that to the bibliography, but like I said, a paper is frozen. I think we finished peer review. But somebody did do it once. We found one paper we did with CMOS, but I still think it's not as cool as this plot that Ben and I made. So basically, CCD, you can find more stuff like this, but for CMOS, we just found, I think, this one paper on this subject where you basically look for hot pixels that are created by radiation. And we actually did the test. This is the percentage of frames in a video of a set period of time, the percentage of frames that have like a random white spot. And you can see it scales. It appears to scale with the amount of radioactivity. And you can see here's our californium source, ambi source, and also different locations. And then here, this right here, Fiestaware plate that my wife bought for $2. It's actually was producing, because it's been decaying for a while now, it's got more radiation than the californium source. And then there's the big guns is our cesium gamma ray sources out here. And you can see there's a trend. But it's not it's random spray, not localized. And so particles are emitted in all directions, and you get like one or two dots. So here, this thing here that looks like the Eye of Sauron, that's our californium 252 source. So, now speaking of radiation, that brings me to another exciting new thing that's, again, not that new, but it's probably new to a lot of listeners, not directly related to UAP. But I've got some proof, and I want to, I haven't mentioned this to Mick West yet. He'll probably just go, meh. But I've got some proof that working on UAPs, even if they're not, craft operated by non-human intelligence, can lead to breakthroughs. So inspired by stories of UFOs and nukes, nuke silos, stories by, Robert Hastings and Robert Salas, I came up with a new idea for a small-scale nuclear reactor. Because, it was during a UAPx meeting. During UAPx Zooming, we're like, hey, can we make like a small nuclear reactor? And then like, you guys, like Lou Alzando has mentioned at some point. But then, I thought to myself after that meeting, UAPx meeting, this was years ago, but it's probably news to many people. Thought to myself, well, could you come up with something? And I did come up with something, actually, that would be completely not, it's basically, the right way to think about it is nuclear power. Basically, I thought of how you can use a process called neutron activation in order to get radiation out of stable isotopes to then just go back to being stable. So it's a really cool idea. I'm really excited about it. Again, because I've been so busy, I don't have, paper on it yet. There will be a scientific paper on it, not an essay, not a YouTube video, but a scientific paper will come out on it. But so far, I've just got this news article here, a Times Union article, local paper. I'm really annoyed because they put safe nuclear power in scare quotes. They put the safe in quotes, and I'm like, are you kidding, guys? Come on. That's just evil. Because when I say safe, I actually mean it, because this has nothing to do with uranium, plutonium. It uses lithium, and it's completely new approach. And then New York Post ran with it and totally over sensationalized it, which is ironic because I know Stephen Greenstreet, who was in A Tear in the Sky, it also works at the Post and is like totally like he's done a 180. He's like completely anti-UFO now. Was like dissing me on Twitter, not by name though, but still he called me a scientist in scare quotes. I'm like, really? He didn't do that by name, but he meant me. And I'm like, okay, I'm a scientist in quotes. All right, Stephen. Yeah, whatever. Okay, I got a PhD from the University of Chicago. I guess I'm a scientist in scare quotes. So I met him and we shook hands on the set. So it was deeply disappointing to see how he went crazy nutso in the opposite direction from UFO crazy nutso of believe everything. He went the opposite direction of disbelieve absolutely everything, which is sad because if he actually would stop ignoring my emails, he'd see like the UAPx paper is actually deeply skeptical and self-effacing and self-debunking. When you get back to my reactor, Professor Kevin Knuth mentioned this during his Soul Foundation talk last year at Gary Nolan's shindig. Not this year's. There was one a few weeks ago, but last year's. He mentioned this on my behalf because I didn't get an invitation, but he mentioned how it was the original inspiration of mine was a small-scale fission reactor to attract UFOs. Obviously, there are much more important benefits: reduction in reliance on fossil fuels, reduction in global warming, and recycling of spent lithium batteries from cars, computers, myriad of other tech. And even though we don't have a paper out yet, but we did see. You can see this is me. This is Bill and Keith. These are professors in my department. This is Andrew, one of my graduate students, and we did celebrate. Because we did not find more power out than in, because that requires funding to build a large scale experiment, but we did see more We saw multiplication of neutrons indicating that we were inducing fission. And you can see here our deuterium beam, which produces neutrons on a sample of a lithium compound. Can't tell you which compound because the patent is still pending. So it's not pure lithium because that's like explosive. That would make it not safe. But yeah, this is connected. So this whole thing with radiation detection of UFOs and also the UFOs and nukes thing inspired something completely unrelated to UFOs. So another thing that's in the works, so we're cooking up this reactor idea. Another thing that's in the works is with help of Mike Swords, Mike West, the Kalamazoo UAP group, if people are familiar with those folks in Michigan. And Robert Powell is sort of is a member there too, even though he lives in Texas. He comes up sometimes to Kalamazoo, Michigan. And basically the idea here is to look for patterns in the colors of UFOs. And the work is still in very preliminary stages and is not ready for a scientific publication. But the idea is to look at the possibilities of Doppler redshift, Doppler blue shift, specifically Doppler blue shift that could explain things like infrared or visible light being wavelength shifted up to ultraviolet. So that was inspired by Eric Davis. And also, speaking of Eric, he's alleged to have worked on crash retrieval programs. That's a hot topic again with David Grush. And I basically have already, so this slide's already slightly outdated because I already have a publication, not a publication, but a preprint of this, where basically I calculate the probability for, okay, we've got smartphones everywhere now, and skeptics are saying, why aren't there pictures? And I decided to do a much more specific thing and not argue about quote unquote a good UFO picture, because what the hell is that supposed to mean? You know, that's ambiguous. I decided to do something that's still ambiguous but slightly less so, which is someone like capturing like a crash, like of an obvious, like it's obviously not a hoax. It stands up to AI scrutiny. You know, it's like could be people from different angles. You could have more than one person, more than one photo or video. And I calculated what are the odds. And so I should have updated this slide. Hopefully, maybe Ben, if I send you later, you could drop this below the YouTube video, but I should have put a link here. I actually have a paper on archive. I mean, my last name is so unique. If you just Google my last name and Google catastrophic disclosure. I forgot to correct this typo on the slide. It's not chaotic. It's called catastrophic disclosure. This is a concept that came up from the Soul Foundation conference. So if you just Google my last name and catastrophic disclosure, exact phrase, you'll find the paper. And I basically calculated that given all the smartphones and given the alleged crash rate, where we don't have proof, but the crash rate that Dave Grush claims for this century at least, I calculated something like by 2040, again with a huge error bar and a lot of uncertainty, we should have like a crash that the Men in Black can't clean up fast enough. It's on a smartphone. The person has a smartphone, puts it on YouTube or TikTok, and it's too late. It's too late. We know that like UFOs are real and they can crash. So I'm really excited that I got such a low number. I thought it was going to take like 500 years since the Earth is pretty big and it's mostly Pacific Ocean. But so I was actually surprised. But obviously it depends on the rate. You lower the annual crash rate, and it would take hundreds of years to get an accidental crash where you can take a picture. So on the topic of crashes again, though, we mentioned this very briefly in the crash paper. I do mention this, is that isotopic analysis can help you determine what something is made of, not just the elements, but the isotopes, because unlike in a lot of science fiction, the universe is the same everywhere. How do we know that? We know that from the light, from spectroscopy. You can do mass spectroscopy to determine what something is made of here on Earth, but that's destructive. So neutron activation analysis is a way of doing a non-destructive analysis, and we came up with a sexier way of doing it. So it's an old technique, it's not new. I'm shocked by the number of people I tell this to who've never heard of it, including Kevin told this to somebody from NASA who didn't believe it works, and I'm like, are you effing kidding me? This has been used for over half a century. So in fact, I just visited Oak Ridge National Lab where they do neutron activation and have been for decades. Mr. NASA guy, who's friend of Kevin's, I don't even remember his name. Otherwise, I might have been tempted to shame him here, but he's lucky I forgot his name. Neutron activation analysis is totally old school. Not a new idea. This is basically where you send neutrons. You make something that's, so you can see this is connected also to the reactor idea earlier. You make something stable, radioactive, temporarily, very safely. So in fact, just to mess with my sister Matilda, who by the way, she plays Zelda in Mrs. Maisel. She's an actress. Just to mess with her because she's afraid of radiation, nuclear, anything, I made a salami radioactive and a cracker, and I ate it. So you might be like, oh my God, I'm going to die of cancer. No, because I waited for the radiation to decay away. So the beauty about radiation activation analysis is most of the isotopes you activate that become radioactive have half-lives of minutes, hours, and so like things will come back to baseline. And so after the cracker, after the salami went back to baseline, I ate it. Now if it didn't go back to baseline and I ate it, yes, that would be very, very, very bad. But I was proving a point of how the dangers of radiation are grossly exaggerated in popular culture and grossly misunderstood what radiation is, what different types are, and things like that. So with neutron activation analysis, you bombard a substance, your test sample. Let's say you've got a piece of a UFO that crashed. You claim you've got a crash flying saucer. We can do a neutron activation analysis, which is non-destructive. That's what's so beautiful, is unlike mass spec, it's non-destructive, and yet it tells you about the isotopes, not the elements, but the actually of the isotopes. So that if their isotopic ratios are off, you could start trying to make claims of like, oh, it's extraterrestrial, it's not from this solar system, things like that. So it's really, really cool, and it's very, very sensitive. We can get down to parts per million, parts per billion level of impurities. So one way to do this is with californium. More recently, I've started doing this with some plutonium that we have. Californium is actually more dangerous with plutonium, but we have a lot less of californium. We have a lot more plutonium on campus, actually borrowed from the DOE. We've got a nice big chunk of plutonium, and so our new strategy is going to use the plutonium instead of my tiny bit of californium. But basically what you do is you expose your source to the radiation. It's non-destructive, so you couldn't even tell. The sample looks exactly the freaking same. But basically you are performing alchemy. Right, that we used to think was possible, with chemicals. It's not, right? We discovered nuclear science, so that's where all the alchemists went wrong for centuries. Is you need nuclear chemistry, not standard chemistry, but we're basically changing some of the atoms inside, not all of them, but just like some sampling, a random sampling of the atoms inside based on how long the exposure is. And then when we watch the decay, we can determine using the half-life as well as the energies. If you can detect the energies of peaks of betas and gammas that come out, you can determine what something's made of. And we thought of a much cheaper way of doing neutron activation analysis than is normally the case. I think usually neutron activation analysis costs like tens of thousands, maybe even hundreds of thousands of dollars to do it well, to do it right at a national lab. And instead, we use a $3,000 californium source and a $300 cosmic watch as our radiation detector. So we use we can do this using the same cosmic watch that we use for detecting UAP radiation. We can use it to force pieces of crash flying saucers. Again, if that's a thing, we're not claiming it is. Again, being agnostic. And in fact, right now, one of the most exciting pieces of news I have, I can't say, I don't want to without checking with those people. I can't say where it's from or what part it is, but I actually do have a sample of a very famous piece of material that's been talked about on like radio programs going back decades, and I'm doing a neutron activation analysis right now on it. I don't want to say more than that because I would want to ask permission, respect the privacy of the people I'm working with on that. But the privacy is temporary. We're going to publish a scientific paper, and I'm going to get that in a real freaking journal. We're not just going to have some lab report PDF that just hides on some website. No, like we're finally going to move forward on UAPx of like publishing more scientific papers, and we're not just doing expeditions. Now we're doing materials analysis for other people. So I'm very excited that right now we've got a sample that's soaking, not soaking literally. I mean, it's not liquid, God forbid, it's a solid. We have a piece of an alleged crashed flying saucer that, again, could be mundane, could be human-made material, but we have it sitting next to what's called a plutonium beryllium source that produces a lot of neutrons. And it's going to absorb those neutrons. We're going to have it sit for several months. So it's going to be then then we're going to look at the half-lives, and we're going to pull out what the different isotopes are in that material. Again, it's going to be hard to claim something's extraterrestrial. What does that even mean? But we'll at least know whether it is interesting. Does it have anything interesting in it that suggests something not of human manufacture? So crashes would be more plausible if Earth is findable. So Kevin has a paper. Again, I forgot to update this slide as well, because there is a link to it. I think his PDF is already online. But Kevin has written a paper already about colonization, and he calculated on average, I think his conclusion was, on average, if there are alien civilizations out there that can find Earth, he calculates, he does a Drake style thing, except much better than that, right? Drake is very old school. Kevin does a much more fancier modern analysis, which isn't just multiply 10 numbers together. It's actually, he ran simulations, he did a Bayesian inference, he did all this stuff, and he figured out that on average, it would take like that if Earth has been found, a civilization that's found Earth probably first discovered Earth roughly 1 million years ago, but with a large error bar. So I'd like to do a follow-up when I have time. How am I going to have time with all these other papers? And add some more features by looking at the entire history of the galaxy over billions of years as it rotates, and look at things like warp drive, which is completely unnecessary. I always stress this to everybody. Because of time dilation, you don't need warp drive. That's another thing the skeptics always get wrong, and it really gets under my skin. But I already beat up on them. I beat up on poor Anne, whoever she is, in Metabunk earlier. But I just want to emphasize this would only be for fun, because I'm a Star Trek fan, and Star Wars as well. So important to emphasize you don't need warp drive because of time dilation. That's standard physics. It's over 100 years old. Go read Einstein's theory of relativity, and or read a standard physics textbook. So time dilation means that you can cross the entire galaxy. This is in Kevin's entropy paper as well. You can cross the entire galaxy in a few months. You don't need 100,000 years. But just for fun, I also want to throw in warp drive and do a paper because I don't think that's been done before. But I'm going to search the existing papers in the SETI community to make sure I'm not accidentally rewriting something, reinventing the wheel, cite what existing work is. But I've never heard of a paper that looks at colonization of the galaxy where warp drive is allowed, or wormholes and things like that. It does like a full simulation of habitable worlds around the galaxy. So, but back to Kevin's paper that, like I say, he's already put out. He's already calculated most probable date of first contact. This is slightly outdated. His talk from this Kavli symposium in the UK is actually, his final conclusion was 1 million, not 250,000 years ago. But again, with a huge error bar, where the most probable first contact date, if there are civilizations in what's called the habitable zone of the galaxy, you can see here a beautiful picture from Kevin. A number of civilizations is the color plot. Basically, one of Kevin's conclusion is that if space is really big, and so if somebody has found Earth, that means there are thousands of civilizations, or millions, but only thousands that are spacefaring. I might have gotten something wrong there because this slide's from Kevin, but you can look up his paper. You can just Google Kevin colonization Kavli symposium, and you'll find the PDF, even though I don't have the link. I don't think it's on the archive. Yeah, so lots of great stuff. Now, I'm throwing this out there, but this is just one aspect of the problem. No, I'm not claiming, all UFOs are aliens, and I'm not claiming that if UFOs are really something cool and weird, like a non-human intelligence, that doesn't mean they're extraterrestrial. Grush said in the Congress, whatever, interdimensional, whatever that means. As a scientist, I really don't like that term, but I'm not claiming ET hypothesis to be all end all, but I'm just saying that this is one of those fun things to explore, and that the SETI community has been doing for decades. So this is one of the things we're going to also be writing some more papers on. So I keep mentioning Kevin and his work. This is another slide from Kevin where he gave a talk at last year's Soul Foundation, where he talked about the extreme electric fields, luminosities, and the extreme speeds and accelerations known since the 1950s in some cases. And Kevin, building on the work of McCampbell and of Mark Roediger, was able to show how it seems plausible that a high electric field from a UFO could stop as well as restart, in some cases, car engines, but not diesel. It's a long story about electromagnetism, and Kevin's, you got to go back and see his talk on YouTube from the Soul Foundation from last year. So the last new publication we want to do is a CTAP one, and as I said, it's really not that miraculous. It's just pixel subtraction. And here's a zoom in that shows you from that earlier example I gave of a distant airplane. You can totally see now, I hope, in this slide at least, like there's something there, and CTAP caught it. And so the beauty of the CTAP software that does image analysis, what it does is it can be used for any kind of image analysis. I've already used it for one of our other discoveries. It's called the snowball chamber. I used to do image processing, video processing for when I worked on bubble chambers as a graduate student. So for particle detectors that rely on visual camera evidence. So it's a very simplistic system. It's mostly pixel subtraction and thresholding. So it's completely non-innovative in that sense, and yet it's so powerful. So it's a sample at left from the UAPx paper that I mentioned earlier. Basically, we want to get, again, on the theme of bridging the gap between, like, how do we get UFOs, UAPs as an accepted field of study, is we need more papers, and we need them in credible, established journals. So the crash paper I mentioned earlier, that's going into Limina. That's Mike Siffone's journal at SUOPS. So that is a new journal. And I'm doing that to help out. Mike's doing a great thing. It's similar to JUFOS, the Journal of UFO Studies that Hynek did, or I think that was out of KUFOS. So Rodinger knows about that history there. Is that, so it's not a new idea to have a UFO-specific journal, but now it's also important to publish in the established journals like we're doing in order to build up credibility with established journals that have high impact factors and site scores already. So something like CTAP, as long as, the editor or the reviewers don't notice that it was born from a UFO project, which would still be unfair if they use that against us. But CTAP may go into a journal, for example, like DSP, Digital Signal Processing. That was Kevin's suggestion. It's something so general. There's just an algorithm for pulling objects out of faint objects in some cases here, like here out of camera images. So final conclusion. So the earlier was a half a conclusion. Now the final conclusions in summary is we're not shying away on UAPx from the most extreme hypotheses, but we're studying them numerically. We're going to continue to look for UAPs no matter how long it takes. It doesn't matter, we would love to have some funding. We're going to limp along with free volunteer time. It probably means no more expeditions, but if we don't get funding, we're going to beat to death the data we already have right now and publish papers and publish tools that other people can use. People with money maybe can go use on their expeditions and on their papers. But most importantly, quality science takes time. So the study of UFOs on an organization like UAPx, many people watching the talk today might be disappointed because the first half at least was all old stuff. But here's the thing. We got to move slowly, carefully, scientifically, and most importantly, boringly. That's what John Oliver said that on a recent show a few months ago. He had an episode on UAP. Gary Voorhees, so this is not Gary Nolan, this is our Gary, who couldn't be here tonight, he's sick. One of his sayings is, I don't know if he came up with it, somebody else, one of his sayings is, less woo, more do. You can get t-shirts on the UAPx website that say that. So what do we mean by that? Do we mean that none of the woo is true? Which also rhymed. I just did it back. No, that's not what we mean, but we mean that when we're not going to jump to conclusions, especially to speculative exotic ones, without going through the careful math and analysis. So we did learn from our first field expedition, even though we didn't have something conclusive, like Ben said, it was probably a fly on the lens. It was worthwhile. It was 100% worthwhile because we gained experience and we're not going to repeat many of those same mistakes. And so we no longer call the presentation here preliminary initial results. These are our final results. So our paper is, as I said, close to done. We're going to publish follow-up papers like on CTAP and things like that. But it's very unlikely you're going to hear from us, oh my God, the dark spot is not a fly, it's a wormhole. That's probably not going to happen. And so we're calling these results pretty final now. This is not our, quote, preliminary initial presentation. So in fact, I was never planning on showing these slides again. I'm doing it because Gary invited me tonight to do this. So this is probably the last time that this giant 2-hour thing will be shown, because in the future will just be miniature presentations on the new stuff. Like, on my crash paper that I wrote and things like that, or Kevin talking about his colonization paper. If we get money for more expeditions, then that's different. then there'll be papers on those. But we're starting to move on. We still might do a full analysis of the FLIR as a citizen science project, get through the many hours of FLIR that CTAP has gone through, but hasn't had human eyes on it again. But I'm highlighting here in bold the final bullet point that we really hope that people will start using some of the benchmarks of statistical significance we suggest in the UAPx paper. And I love this joke from a random scientist, I don't even know in what field, named Dr. Dave Nelson. And I love his suggestion of we should use these emojis. I think this is hilarious. The like Pinocchio nose, the smiley, and this for what's the p-value that goes with the sigma value. So for people who don't know what sigma and p-values are, who are listening to this, I know they'll be totally confused. But basically, the smaller value here means something's less likely to be a statistical fluke and is an actual anomaly. And a higher number for this thing, which is the Greek letter sigma, it signifies the same thing. There's just a couple different ways of doing statistical analyses. So, this is outdated because this course is over, but I'm probably going to teach it again next summer, so maybe it's not outdated. So I taught a course on exotic propulsion for Society for UAP Studies. I'm going to try to do it next summer, so everybody should sign up and tell their friends. We had a great time. It's online, and questions, email me, but please don't email me with your, dear Mr. Shadagius, I saw a UFO last night. Like, I'm like, okay, you can tell MUFON, rest of you, don't send us your photos and videos because there are organizations that already do that. Remember, the focus of UAPx is to get our own data. So maybe you've got the smoking gun and you've got your kick-ass UFO video, great. But there are existing organizations that handle that, like the SCU will do analyses of videos from pilots or from astronomers or from any civilians. But it's got to be serious. You've got 2 pixels in the corner, and it's like, yeah. So like, email me if you have a serious question, about like tonight's presentation, then please do. But don't email me a 10-page story about how aliens abducted you last night, because if you don't have proof to back it up, again, we're not interested, because we want to get the hard evidence on UAPx, and we know how hard that's going to be. We understand the challenges of reproducibility. But here's a quote from Freeman Dyson, very famous scientist. The great advances in science usually result from new tools rather than from new doctrines. So why do I end with that? Because UAPx's philosophy is very different from many other UFO groups who would disagree with that Freeman Dyson quote and are looking for new doctrines like, oh, it's the extraterrestrial hypothesis or this or that. And our approach is tools. Deploy detectors, look for weird shit in your tools. And so other UFO organizations will have a different philosophy. That's okay. I can't prove to you this is the right approach, new tools rather than new doctrine, just because a famous person said it in 1996. But that's why I think it's important to have different approaches. So with that, I will conclude, and I will turn my camera back on, and I'll be happy to address questions.
Alrighty, we do not have any questions in the chat. So thank you so much, Professor. That was awesome. It's always a treat to have you on Space Oddities, and hopefully everyone, if anyone has any questions, they'll reach out. It's a great presentation, and it'll only get better as we get more funding and can develop those tools you're talking about.
Yeah, we'll limp along for free and publish the analyses, but we can't do expeditions to get new data. But we can definitely, there's still more old data to analyze, like the rest of the FLIR. But yeah, we're going to limp along, and without funding, that's the best we're going to be able to do, is like a paper every 4 years when we have free time. But yeah, hopefully, someone out there is listening, and somebody decides this is the UFO organization that has the right people and the right tools, and it's worth investing money in. All right. Is that it for tonight then? Should we sign off, Ben?
I think we should sign off. We've been going for 2 hours, so thank you again, Matthew. Thank you all for joining us, and we will see you on the next episode of Space Oddities.
All right.
Good night.
Yeah, good night.